Hello and welcome to a new session for this online course on Introduction to Embedded System Design. I am your instructor Dhananjay Gadre. In this session we are going to talk about one of the peripheral functions of a microcontroller, namely communicating with the outside world. Now if you want to communicate, a microcontroller wants to communicate with the outside world, there are many ways of communication, but the common methods require you to send the data and receive data in a serial fashion. Why? Because it minimizes the number of connections that you would require for communication. The data in a microcontroller or in any computer is in the form of bytes or words, and so if you want to transmit a byte of data, otherwise you would require 8 bits, that is 8 wires, one for each of the bits, and then ground and some other handshake signals as they call it. So, the number of wires that would be required to connect between two devices would grow too much, and this is not preferred, and therefore, any communication that normally happens is in the form of a serial form, that is the byte or word that you want to transmit is serialized one bit at a time and transmitted, similarly it is received in that fashion. So, in this lecture we are going to look at the various methods of communication with the outside world, meaning with other devices which have similar capabilities of communication. How do we get our MSP430 microcontroller to communicate with them? Now, this is defined as communication protocols. Communication protocol is simply a set of rules and formal descriptions which are defined for communicating information between two devices. In other words, this communication protocol defines the format of the data that will be sent, because you are sending parallel, you have parallel data, but you want to send it serially. So, you have to decide what is the format of that data and at what rate are you sending each of these bits. A communication protocol basically defines these rules. Now, when we communicate between two devices, let me draw them here. For example, if I want to communicate between device A and device B, and this could be electronic devices, humans and so on and so forth. Let us say this is A and B and you want to communicate between them. If you only transmit between from A to B with no possibility of B responding to you, this would be called simplex mode of communication. Then you could have half duplex, in which yes, it is possible for A to communicate information to B as well as for B to send back information to A, but not at the same time. This is called half duplex. And when you have full duplex, which means when you transmit from A to B and B to A, and these two transmissions can happen simultaneously, this is called full duplex. In real life, in normal life, we have examples. For example, simplex communication happens if you are talking to somebody and there is no mechanism, for example, radio transmission, broadcast transmission. Suppose you are listening to FM channel, the transmitter is transmitting and you only receive. On the other hand, half duplex is what normally happens using a walkie talkie. There is a button called push to talk. The one who pushes that button is able to transmit, the rest everybody can receive, and then when they want to talk, they push their push to talk button, then they talk and the rest of the receivers can receive information. And full duplex is what happens when you make a telephone call. Both the people can talk at the same time. Of course, in the case of humans, both people talking at the same time, they may not listen to what the other person is saying, but that is a different matter. So, there are three modes of communication: simplex, half duplex and full duplex. Now, on our MSP430, we have several communication protocols, several serial communication protocols, and the most common of them is the UART. It stands for Universal Asynchronous Receiver and Transmitter. Then we also have a mechanism for higher speed of communication. This is called Serial Peripheral Interface, and the third method is called I2C, which is inter-IC communication. We can think of these, you may recall that when we were talking about the 6-box model for embedded systems and we considered the various communication methods, we classified the communication methods in two ways. One was called communicating within a device, and we call that intra device communication. And then we had another mechanism called inter device communication, that is, if there are two individual independent entities, if they want to communicate, what kind of protocols are suitable for communicating between two independent devices, and we call that inter device communication. Now, UART typically is suitable not only for intra device, that is within a device, if there are devices within a, if there are building blocks within a device, they want to communicate serially, you could use a UART. It is suitable for that, and it is also suitable for communicating between two independent devices. So, it is also suitable for inter device communication. SPI and I2C on the other hand are most suitable for intra device communication, intra device communication. And we will see what all where all these two protocols are used. Now, UART is the most common method of communication between a microcontroller and another microcontroller, or a microcontroller and a desktop computer, or many other examples. In fact, you are using UART every time you connect your MSP430 lunchbox to your desktop computer. It is using, although on the desktop side it is using a USB interface, but on the microcontroller side the USB protocol is converted into a UART protocol, and appropriate pins of MSP430 which are able to communicate using the UART, you make that connection, and that is how the program is being downloaded from the desktop computer into the memory of the MSP430 lunchbox microcontroller. UART uses dedicated hardware and it is communicating in a serial fashion. When you are transmitting data serially, you had to decide what is the duration of each data, because each bit, because we are saying the communication type is asynchronous, which means there is no accompanying clock with the data that is being sent, and therefore some other method of knowing when one bit ends and the other bit starts, the next bit starts, has to be decided, and one method of doing that is to finalize and agree upon a certain time for which each bit will last, and this rate, the resultant rate, is called bit rate or baud rate, and the user has to define this before any communication can happen. And of course, both the devices must agree on that bit rate or baud rate. Also, since you are sending data serially, for historical reasons, in the olden times you did not want to send 8 bits of data. In fact, if you recall, ASCII standard is defined for 7 bits. The original ASCII standard is 7 bits. So, if you wanted to send ASCII information, you only want to send 7 bits. But these days you want to send entire 8 bits of data, and in fact ASCII, there is a advanced additional ASCII format which allows for 8 bits, and so you may choose to decide how many data bits will be sent in each transmission, and together with the rest of the bits we call this one data packet, and this consists of one start bit, between 5 to 9 data bits, and then you can also have a parity bit. The parity bit allows you to detect whether in the transmission of the data bits if there has been any error because of noise. It does not tell you which bit went wrong, it will only tell you if any bit went wrong, and it can only tell if one bit went wrong. If 2 bits went wrong, the parity error may not be able to tell you that possibility. And then after the parity bit you can add 1 or 2 stop bits, and there is a method of specifying the format of your communication. As an example, you could say that we are going to communicate at 96008N1. I will explain what this what these numbers mean. So, the first value is the bit rate or baud rate as they call it often. Then the second value is data bits, number of data bits that you want to transmit. Then the information about parity, and the last is the stop bits. There is no option of specifying the number of start bits. the information regarding start bit is fixed and it is only one start bit per packet transmission. And so, if I say my format is 9600, 8, n, 1, that means my bit rate is 9600 bits per second. I want to transmit 8 data bits per transmission. I do not want to have any parity. The options are, so bit rate we will see what are the various options. Standard bit rates are available. Data bits can be 5, 6, 7, 8, and in some microcontrollers it also offers 9 bits of data. The parity bit, there are 3 options: no parity, odd parity or even parity. And for stop bit, historically it offers 3 options: 1 stop bit, 1.5 stop bit or 2 stop bits. In the case of MSP430, you have the options of 1 or 2, and you can choose whether you want to have a parity or no parity at all, and if you want to have a parity, whether it is odd parity you want to include or even parity. Here is a list of standard baud rates. Now, the meaning of standard baud rates means that if you have an existing device, let us say a standard laptop or desktop, which would offer certain serial communication protocols, it would offer the communication rates which can be from one of these numbers. Of course, if both the devices that want to communicate using the UART protocol and both the devices are your devices, you can choose arbitrary rates of communication. There is nothing wrong with that. But if you want to communicate with existing devices, then these are the standard baud rates that you must choose from: 300 bits per second, 600 bits per second, so on and so forth. If you see, there is a factor of 2 as you go down this list, the number of data bits per second, they double, and the maximum bit rate you can get is, there is a 0 missing here, 115,000. Okay. So, these are the standard baud rates that are available, and these baud rates, because, so if I say 9600 bits per second, that means each bit is going to last for this duration. The value of bit time is equal to 1 by the bit rate. So, it is 9600, and in this case this becomes 104 microseconds. Now, because there is a timing information involved, there has to be a mechanism for the microcontroller to generate this timing information, so that it can change each bit after 104 microseconds. And of course, the microcontroller has timing information in the form of various clock signals. In the case of our MSP430, we have A clock, we have SM clock and we have M clock, and we can choose which of these clock signals will provide the timing information necessary for serial communication. Now, the basic block diagram of communication between two devices is illustrated in this diagram. You have device 1 and you have device 2. The 2 pins of serial communication are called TX, or oftentimes they are also called TXD. I could also call this TXD, and the other pin for receiving is called RXD. So, you have to connect the transmitting bit to the receiving bit of the second device and vice versa, and of course, you need a common ground connection. So, these are the 3 pins that are required for, minimum 3 pins that are required for communicating between two devices. Whether one device could be a microcontroller is fine, it could be a microcontroller, and the other device could be some peripheral, or you could have both the devices as microcontrollers. It could be 2 independent devices, they would want to communicate with each other, it could use the UART protocol. Now, if the distance between these 2 devices is small, of the order of few inches, then you can simply take the transmitting pin of one device and connect it to the receiving pin of the other device, and all this would work fine. Of course, the logic levels on these pins must match each other, which means if this device is powered at 5 volts, then the second device should also be powered at 5 volts. If this device is powered at 3.3, the other should also be powered at 3.3. Now, as the distance between the 2 devices increases, and if the 2 devices are not being operated at common or identical supply voltages, then making such a connection may not result in reliable communication. And therefore, some sort of line drivers, that is some sort of amplifiers on these lines will be required, so that the distance between the two devices does not induce noise in the data that is being transmitted. And based on the type of line drivers that you include will lead to different types of protocols. We will see what are those protocols that are available. Now, when you transmit the data, as I mentioned, at the beginning of the transmission, the logic on your output pin is logic 1, and when the device is ready to transmit, it will take the TXD pin, it will take it low for a certain amount of time equal to bit time, and then depending upon the value of the actual data bit, bit 0, that bit can go high or it can remain low depending upon the value of D0 and so on and so forth, and you are going to transmit D0, D1, D2 all the way till the last bit, and then depending upon the parity bit, that is the parity of these bits can be stuffed, can be added at the end of this. After that you will add a stop bit which is of a logic high, and then when the stop bit ends you can start a new transmission. This is the format of data that is serially transmitted between one device and will be received by the second device. As I mentioned, we need line drivers so that data is effectively and noiselessly communicated from one end to the other end, and one protocol which is very popular is called RS232. It requires line driver like this on this side, and this here simply means that the distance between the transmitter and receiver can be large, and then you need to have a line receiver IC or line receiver amplifier. As you see here, this line driver also inverts the logic, that is if you send 0 here the value will be inverted, but the voltage levels at which the RS232 line drivers work, they operate as follows. If the input is 0, then the output RS232 is plus V, some voltage V. If the input is 1, then it is minus V. And what are these voltages? The value of V could be anything greater than 3 volts and less than 15 volts, which means this line driver and similarly this line receiver has to have a separate power supply. For example, let me give an example. Your microcontroller can be working at 3 volts, and the RS232 line transmitter and line driver and receiver can work at plus minus 5 volt or plus minus 10 volt. Now, how do you generate plus minus 5 volt from 3 volts? Either you supply individual voltages, bipolar voltages of this value, or many of these line drivers have a mechanism, have a built-in DC to DC converter which converts the supply voltage of 3 volt to 5 or 10 volts. Standard line driver ICs, transmitters and receivers are available. For example, there is an IC called MAX232. This will convert the TTL or 3 volt logic levels into RS232 protocol. On the receiving side, it will receive the bipolar voltages and it will invert the logic, and again it will give you the same logic level as required by this device. So, this is, let us say this is device 1 and this is device 2. Remember that this transmitter and receiver here are connected to this device. So, they may share the supply voltage from device 2, which could be 5 volts, this could be 3 volts. This driver and receiver is connected very close to the device 1 and it may have a different supply voltage, it does not matter. What matters is that the voltages on the RS232 signals will conform to these levels, and they may be different, and yet these two devices, these two line drivers and receivers will convert the RS232 levels into the logic levels corresponding to the actual device on their side. Using this protocol, using this method, you can have standard baud rates going up to 115 200, that is 115,200 bits per second. You can have the distance between the transmitter and receiver to few tens or hundreds of meters. Now, as the distance between the transmitter and receiver increases, the possibility of noise corrupting the data increases, and one method of reducing that noise is to have a different kind of line driver and receiver, one that is called as differential transmitter and receivers. It leads to a different protocol, and that protocol is called RS422. But remember, our UART here is still the same. It also has the same data format. Voltages are also the same, but the voltages that are available on these lines, the serial communication lines, now conform to RS422 format. Here the line driver has a true and a inverted value, and these are again received by the receiver. It takes the difference of these two voltages, and any common mode noise that may have corrupted the two data lines would be subtracted out, and you would get your actual value back here. And so, these differential these are called differential transmitters and receivers. They are able to communicate between two devices for a longer distance and a higher bit rate. Now, in all these discussions till now, we have seen that there is only one transmitter and one receiver, that is, there is a transmitter on one end and receiver on the other, and the other side has a transmitter and receiver. This allows for up to full duplex communication. And what if you wanted to communicate between more than two devices? Like here we have device 1 and device 2, what if I wanted to have one more device? Using these protocols, it is not possible, but there is a modification and there is a new method, a different method called RS485. It is a derivative of the RS422, except if you see here, now the line driver not only has a differential output, but it also has an enable pin. You see here, it has an enable pin. Now, if the pin is not enabled, the line driver would tri-state the outputs, meaning it would disconnect it from this cable. Similarly, the receiver has these two inputs connected, and of course, if the transmitter is not transmitting anything, it will receive the value from somewhere else. Now, using this enable mechanism, you can connect multiple devices. Now, the moment there are multiple devices, question arises as to who would be transmitting, because we still have a common set of wires, and therefore, at any time only one person can transmit. If more than one device transmits, it would lead to what is called as data corruption. It will lead to collision of data, and you do not want collision of data, and therefore, one method of saving that possibility is to have a master slave protocol, where there is a master, the master would decide which slave can communicate back, and this method is usually what we have in a classroom. The teacher is the master and all the students are the slaves. The teacher can allow a particular student to ask a question, and till the permission comes, nobody can ask a question. And using this protocol, you can have multiple devices connected to each other to create a sort of network of microcontrollers. You may recall that in India there is a very popular program called Kaun Banega Karodpati, Who Wants to be a Millionaire, international version of that program. In that, you see many of these participants, they offer a vote. They are able to vote based on the person requirement of the person on the hot seat. How do they communicate their vote? You could implement such a network using RS485 protocol, where each of the viewer or each of the audience in the hall would have a keypad on their seat, which has 4 pins, 4 keys A, B, C, D to offer the options, and all these chairs could be networked using RS485 protocol, and it could be received at the desktop computer of the host to get the information of the votes, and a simple network made out of RS485 can easily satisfy the requirements of audience voting, audience poll in the case of such a requirement. Now, what are the steps of transmission? When you want to transmit data, you have a microcontroller, that is the CPU, and you have the UART. Of course, in a microcontroller, this is your CPU and this is your UART. Both of these these building blocks are integrated in the same chip, but the CPU will transmit information of the data that it wants to transmit from the CPU to the UART. The UART will add the start bit, then it will send the start bit, it will serialize the received data. At the end of it, it may add a parity bit as well as stop bit, and this data will be sent on the TX line, TXT. In the case of reception, you reverse the format. Now, the UART is going to receive data from a transmitter here. It is going to come into the RX pin, and this will communicate to the CPU. This is your CPU, this is your UART. The UART will receive the start bit, it will start receiving the data bits, and then the parity and the stop bit. It will strip off the start bit, parity bit and stop bit. Of course, it will use the parity bit received from the transmitter and compare it with the locally computed parity bit. If they two match, that means no error has been encountered in the transmission, and then it will remove the data bits and present them to the CPU. This is how the reception happens. So, this is as far as the UART protocol is concerned. The second protocol that is available on MSP 430 is the serial peripheral interface. This is a full duplex synchronous. The previous protocol was asynchronous, which means there was no separate clock that was being sent, but here you have to send a separate clock, and you can create a network of devices using SPI, and you have a master, and you can have one slave or multiple slaves, and you can have full duplex communication. This is the signal connections between a master and a slave, or you could have multiple slaves. You have MOSI, that stands for master out, slave in. This is the receiver part, master out and slave in is on the slave is a receiving pin. Master in slave out is a receiving pin on master, but it is a transmitting pin on the slave. Then you have a serial clock which goes from the master to the slave, and you have a chip select which enables a particular slave. So, if you have multiple slaves, you would need multiple chip select devices, so that you can select which slave you want to communicate with at any given point of time. The timing diagram of the various signals, that is chip select, serial clock, MOSI, MISO, is shown here. It starts from the master, and then once the master has sent the data here, this is the data being sent by the master. The MISO at that time will be in high impedance state, and once the data has been transmitted, it may expect the slave to respond back, and this is the data received from the slave. In this way, you can have communication, full duplex communication, and this can overlap. You can also have data being transmitted from the master to the slave at that time, synchronized with the clock signal. And using this, one or multiple devices can communicate with a MSP 430 or similar microcontrollers. The clock rate is quite high. It can go up to 4 megahertz or even more, and therefore, the data rate of communication between two devices using the SPI protocol is much higher compared to the data rate that you get on UART. But remember, SPI is not used for communicating between two devices, it is used for communication within a device, between the microcontroller and a peripheral device. Now, the advantages and disadvantages of this protocol are listed here. Since there is no start and stop bits, the effective number of bits is does not have that overhead. So, your data rate will be higher. You can support multiple slaves. but you can't use this for long distance communication between two devices, and if you have multiple slaves it will require multiple chip select pins from the master. That is the only disadvantage of this method. The third method of communication that MSP430 offers is called inter-IC communication. As you see here, it is called I2C. It is a half duplex communication protocol, and you can connect multiple devices, multiple slaves to the microcontroller, and you can connect up to 7 additional devices. That is the beauty of this protocol. The communication rate is not as high as you would get on the SPI, but higher than what you can achieve on the UART, and therefore, this is very preferred when you have to connect multiple devices and you do not have many pins, because on SPI bus you can connect many devices, but as you increase the number of devices, the number of chip select pins will linearly increase. That is not the case with I2C. Here is what is required. You only have 2 pins, one is called serial data and the second is called serial clock. The clock starts from the master, goes to the slave, and the data is bidirectional. The master starts the communication, the slave receives it, and then if required the slave can respond. Now, if you want to have multiple such devices, you can connect them to the same pins in the following way. Here is your master, this is your master, and we are talking of I2C protocol. You could have slave 1 and up to slave 7, and using only 2 wires, and let me draw the second wire with a different color you can have, and you would of course need a pull up resistor on both of these wires. Now, how does a particular slave get selected? Well, each of the slaves has an address. Master address is 0 and then you have slave address from 1 to 7, and the transmission includes the address of the slave. And how does the slave know its address? Well, in many of these, if this is a peripheral IC, it would have a mechanism, either that address is hard wired into the IC, or oftentimes there are 3 address lines, and you can set these 3 address lines to any particular combination that you would like to have. Here is the timing diagram of communication on the I2C bus. You have to initiate a start condition, which is when the serial clock pin is high and there is a high to low transition on the SDA bus, and then you have certain number of bits, and then you end that transmission with a stop condition in which the clock pin is high and you have a low to high transition on the SDA pin. This will terminate that channel, that packet of data, and the slave can then respond. Only 2 devices, 2 pins, 2 wires are required, so it is an advantage, and you can have a master and multiple slaves, but the rate of communication is much slower compared to what you can achieve with the SPI. Now, let us look at the serial communication capabilities within MSP430 in the context of these 3 protocols, and we will see how the peripheral serial communication peripheral on MSP430 allows you to select one of these 3 protocols and so on. Now, there are 2 serial communication interface modules in MSP430 G2553 that we are using, and they are called universal serial communication interface. The reason why they are called universal, because each of these modules offer multiple protocol, there is support for multiple protocols. The A0 module offers UART, it has an infrared data communication as well as a LIN protocol and the SPI mode, and whereas the B0 module offers only the I2C and SPI mode. So, if you want to have one UART and one I2C, it is possible. If you want to have 2 SPI, it is possible. If you want to have one UART and one SPI, it is possible. So, combinations of these protocols can be implemented on MSP430 microcontroller. Now, for UART, you have to use the A module, A0 module, and it uses 2 pins. Those 2 pins will be listed on the microcontroller as RxD and TxD. Of course, these pins are mapped on available port pins. The module can send 8 or 7 or 8 bits of data with odd, even or no parity. It has independent transmit and receive shift registers, which is how it is able to communicate in a full duplex fashion. Remember, you are sending parallel data from the CPU to the peripheral, and the peripheral converts that parallel data into a serial bit stream. So, essentially the UART interface acts like a serial register, meaning either it works parallel in, serial out for the transmitter, and for the receiver it is like serial in, parallel out. You can decide whether you want to send the LSB first or MSB first. The standard method is to send the least significant bit first. You have programmable baud rate, which means you can change for given clock signals available on your microcontroller. You can change the bit rate to support any of these standard bit rates. There is a mechanism to exit the low power modes once serial communication data is received. There are flags which detect if some error has happened in the communication, and there are independent interrupt capabilities for receiving and transmitting functions of the universal serial communication interface on MSP 430. Here is a block diagram. Let this block diagram not intimidate you. I am going to go through that. So, you see the most important part is the part which is the baud rate generator here. It has a possibility of selecting a source of clock. There is an internal clock generator. You could choose, or you could choose the A clock, auxiliary clock, or you could choose the SM clock. This, with the help of certain registers, will divide the clock frequency down to get the bit rate clock. Now, this clock is shared to the receiving section as well as the transmitting section. In the receiving section, the data that is coming from the Rx pin goes into the shift register, and once the data is received, it is transferred to the buffer receiver buffer, and then the microcontroller will get to know that a data byte is available on the receive buffer, and then it can be transferred to the CPU. On the transmitting side, the CPU writes data into the transmit buffer. From the transmit buffer, it is transferred into the shift register, so that the data is serialized and sent out through the TX pin. That is essentially the entire simplified explanation of how the UART module on MSP 430 works. Of course, to be able to do that, it requires many registers, and we will just go through those registers. The UART format, as I mentioned, can be D0 down to the last bit, and then you have parity bits and so on, and stop bits. You have a baud rate selector. There are 3 register: baud rate 0 register, baud rate 1, and a modulation control registers. And the values that these registers must be initialized, the user manual has a useful guide which tells you if this is your clock source and you want to communicate at certain baud rate, what should be the values that you should load into the baud rate register 0, baud rate register 1, and the modulation control registers. Here are examples that if your clock is 32768 and you want to do at 9600, what values should be stored in the baud rate registers and the modulation registers. Then once you have you want to transmit data, you can do that with the help of an interrupt. There is an interrupt vector for transmit, which means the moment the output buffer is empty, it will generate an interrupt to the CPU, and the CPU can then load a new value into the buffer, and there is a flag, interrupt flag, which tells whether the transmitter is ready, and you can also enable and disable this interrupt. You also have a independent interrupt for the receiving function, and whenever the interrupt flag is set, that means a new character is available in the buffer and the CPU can read it. The interrupt request is generated if this flag is 1 and you have enabled the global interrupts, and you reset it by resetting this flag, and it is also reset on power up clear condition. And this flag is automatically reset when you read this buffer register. So, when you read it, you do not have to clear that flag, the flag interrupt flag is automatically cleared. These are the various registers for UART module. There is a control register 0 and 1 for A0, there is a baud rate register, as I mentioned, baud rate register 0, 1 and a modulation control register. This status register will tell you what is the state of transmission and reception, whether a new byte has been received or the old byte has been transmitted, if there is an error in those transmissions. Then you have a receive buffer and a transmit buffer. You have there is a mechanism to automatically detect the baud rate of incoming data, and you can use that. Then there are registers for infrared communication, and then you have interrupt enable register as well as interrupt flag registers. I strongly recommend that you go through these slides to understand the operation of the control register. For example, here you are selecting whether you want the parity to be enabled, do you want the MSB first or the LSB first, what is the size of the data transmission, 7 bits or 8 bits, whether you want a 1 stop bit or 2 stop bits, whether you want to operate in a UART mode and so on, and whether you are doing synchronous or asynchronous mode of communication. Then the control 1 register allows you to select what sort of clock source you would like to have and so on. Then these are the baud rate registers, registers 0 and 1. We will see a code example to understand this these registers better. You have the modulation control register. The modulation control register is there so that the baud bit rate which is generated by dividing the system clock or whatever clock source you have chosen, if there is an error, then the modulation control register will allow you to minimize the effect of that error. This is the status registers, status register which tell you whether data has been, whether there is a parity error, whether receive any other error on the receiving function and so on. Then these are the receive buffers here and the transmit buffer registers, so that you can receive and transmit data. These are the two registers in which you are going to write data for transmission and you are going to read that register whenever serial data is received. You have the interrupt enable register 2 and interrupt flag register 2. You can disable or enable those interrupts through these registers. And here is now, as I mentioned, the transmit and receive pins are shared with port pins. In the case of MSP430 G2553, the transmitting pin is on receiving pin is on P1.1 here, P1.1, and the transmitting pin here is on P1.2. So, you have to the direction is automatically determined when you write into the USCI register, but the cell 1 and cell 2 bits you have to, for RxD you have to write 1 and 1 here, and for transmitting also you have to write 1 and 1 here. Once you write these registers, you are set. The two pins P1.1 and P1.2 are configured for receiving and transmitting serial data using the UART. By writing appropriate numbers into the baud rate registers, you have decided the baud rate. By writing into the interrupt registers, you have decided whether you want to have interrupt on transmission or reception, and by writing into the other control registers, you are set. And then let us see an example. What we are going to do is, we are going to take the MSP430 lunchbox, we are going to communicate to a PC. On the PC, we will show what kind of software you should install, so that you can transmit data from the PC. You type any key on the keyboard of the laptop or desktop, that value will be encoded, serialized and sent, and the microcontroller MSP430 lunchbox will receive it. It will increment the value and send it back. And the reason why we have chosen to increment the value is so that if by mistake the Rx and Tx pins are shorted, if you just use a echo function, that is, if I send A, I should get back A. That is, if here is your PC, let us say here is your PC, and from this PC, if you, this is your microcontroller, this is the transmit pin, receive pin. If by chance they get shorted, then if this fellow sends a value, it will be received back, and you might think, oh, it is working fine, but it could be because the pins are shorted. So, I do not recommend a echo function. I have a modified echo function, which means whatever value is sent, I increment it and send it back. And if you transmit information using the ASCII protocol, you know that the code for A, if you add 1 to it, you get a ASCII code for B. If you send 1, you will get 2 and so on. So, this is a very good test. Visually you can decipher whether the values that you are transmitting, whether they are being received properly or not. Let us go through that. It is just a single page of code. You have in the main program, all you have done is you have reset the stop the watchdog timer as we always do, and then we are calling a subroutine for setting the UART registers. Here is that register. In this, the P cell 1 and P cell 2 bits are written appropriately, so that you can map the transmit and receive functions on P 1.1 and 1.2. Then you have chosen to use the UART clock from ACLK. In our case, the ACLK is coming from the low frequency crystal oscillator, that is 32768. The bit rate values are stored in these two registers, a value of 3, that is 32768 divided by 9600, you will get a value of 3.41. So, this 3 you are writing into one of the registers, this 0.41 into 8, the resultant value you write into the modulation register here, the 3 value, and then you initialize the UART module by writing into the control register, and then you enable the receiving interrupt. So, what we are doing is the MSP430 lunchbox is once it is programmed, it is waiting for a byte to be received from the transmit from the external world, in this case the PC. Once that value is received, it will see what it does. So, once the once the UART is programmed, then it just sets the registers in the status register to enable the global interrupts, and when a byte is received, it will generate a interrupt vector. Here we are going to go into the receive vector. In that receive vector, we are waiting that we have received a byte, but since we want to increment and transmit it, we want to make sure that the transmit buffer is available. So, wait if the transmit buffer is not available. Once that is available, you simply write into the transmit buffer the value that you get from the receive buffer plus 1. This is the entire code. I strongly recommend that you build and download this code into your MSP430 lunchbox. Now, there is a little catch here, because our MSP430 lunchbox, since we are using the bootloader mechanism, the pins for bootloader serial communication are different from the two UART pins, that is TXD and RXD. So, we have jumpers on the MSP430 lunchbox, which you must modify after you have downloaded the program from the laptop or desktop into the lunchbox. Then you should remove the jumpers and place them in the appropriate location, which I will show you in the next photograph, and then you should invoke a program on your laptop, which I will show. So, first of all, this is the jumper settings, as you see here. For programming, download the program from the desktop into the microcontroller. The jumper settings, there are 3 pins here in this, these 2 should be shorted when you are downloading the program. Once the program is downloaded, you have to remove these shorting jumpers and you have to connect them on this side, on these 2 sides. Now, your microcontroller is ready to communicate with the PC using UART. And what do? You install a software called PuTTY. PuTTY allows you to select the baud rate and the rest of the data bits, and then when you have initialized it and when you transmit, this is what it receives. So, we sent A, we got B, we sent B, we got C, and so on. So, if you send A, you will get B, if you send B, you will get C, if you send a capital A, you will get capital B, and so on. If you send a 1, you will get 2, and so on. So, if this works on your PuTTY, on your laptop or desktop, that means congratulations, the microcontroller is working as expected. It is communicating with the PC at the rate of 96008N1 protocol, and of course, you can experiment with other bit rates to see whether that is possible. So, in this lecture, we have seen how MSP430 microcontroller can communicate using a variety of protocols, but because of the limitation of the coverage that we can do in this course, we have restricted ourselves to communicating using only the UART. You are free to read the data sheet to understand how the SPI and I2C bus works, and you could use your MSP430 for communicating with external devices within the same microcontroller system, embedded system, to utilize the SPI and I2C bus also. And you can use the UART to communicate between two microcontrollers or between one microcontroller and one PC, as we have illustrated here. The code example that we have shared can be extended for use between two microcontrollers and so on. So, with this I finish this lecture here, and I will see you soon with a new lecture. Thank you.